The next application is blending applications. Blending problems are where you have several resources or ingredients that are mixed together to produce the end products. The end product uh, usually will have certain minimum quality requirements that need to be met. And blending problems are usually minimization problems. And we saw one such problem in the previous chapter, the minimization problem. And here we're going to look at two blending problems. So blending problems are common in chemical industry where you mix different ingredients, chemical and petroleum industry as well, where you mix different ingredients to produce a final end product. So this first application is a diet preparation application where we have a cereal company that mixes three different grains to produce a cereal, and the cereal properties are given here. There are three different the grain properties. There are three different grains. Those are the ingredients, and they cost these number of cents per pound. And there are the final end product is evaluated based on four requirements, and those are protein, riboflavin, phosphorus, and magnesium. And the amount of units of each of those four uh, outcome measures, okay, in each of these grains is given in this table, and based on the US recommended dietary allowance, etc., the company has determined that each 2-ounce serving of cereal should contain 3 units of protein, 2 units of riboflavin, 1 unit of phosphorus, and 0.425 units of magnesium. Okay, so you have to mix these in such a way that you get 2 ounces of final product and the cost is minimum. And when you figure out how much protein, riboflavin, and phosphorus and magnesium that 2-ounce mix will have, that should meet these requirements. Okay, so that's the blending problem for us. Okay, let's head on over to Excel. Okay. Let's set up the minimum requirements of how many units of each of these four different nutritional aspects that the cereal should meet. Okay, so these are the units. Okay, so let's see. Those are inputs. Okay, let's put a borderline there. Okay, and serving size is 2 ounces. All right, so that also is input. Then we have for each of the three grains A, B, and C, we have cost and then how much of each of these four different nutritional elements that the grain has per pound, right? So that information is given in the table that we just saw. Okay, and that's this information. This is also input. So let's put a borderline there. All right. Okay. So now the question is, how many pounds of A, B, and C, the grains, you will mix, okay, to produce 2 ounces of the blend. So which means that these pounds are going to be fractional amounts because they should amount to 2 ounces. Okay. So this should be the changing cell. Okay. Now let's do the serving size constraint first, so that way we'll know exactly what's going on. So the serving size must be 2 ounces, right? But then the grains are in pounds. So we have to convert this 2 ounce into pounds. So what should we do? 16 ounces per pound. So 2 divided by 16. So your serving size must be 0.125 pounds. So that means when you sum this, okay, the pounds of A, pounds of B, and pounds of C, okay, that should what? Less than or equal to or greater than or equal to? Well, actually, we want it to be exactly equal to. Serving size here, it cannot be more or it cannot be less. So you have to put a label equal to, but Excel, if you put equal to in Excel, Excel will think it's a formula and it will expect a formula. So how do you force Excel to accept equal to sign as a label? Well, you put a quotation mark, single quotation, and then you put your equal to, then Excel will treat this as a label and let you enter the equal to sign. So set it equal. Okay, so now we have taken care of the converting pounds into ounces, or actually we converted the ounces into pounds. And this is going to make sure that the output is exactly 2 ounces. So now the required of each of these, okay, US RDA recommended required, okay, and the actuals are some product of how many units per pound and how many pounds of the grain that we use. How many pounds of the grain we use must be absolute referenced. Okay. Now that should be greater than or equal to. So these are minimum required levels. Okay. Now cost per serving is then some product of cost per pound with how many pounds of the grain that we use, and that is the that's the objective function. So now we are ready to solve, right? So cost per serving should be minimum, and by changing cell is that. The constraints, these must be greater than or equal to these must be greater than or equal to that. Add, and this must be equal to that. Then we are done. Well, we have to make sure that this is selected and simplex LP is selected as the solving method. And now we have 0.025 pounds, 0.05 pounds, 0.005 pounds gives you exactly equal to 2 ounces, and 5.075 cents. Okay, these are in cents, so that's the cost of our mix, and we meet all the requirements. So here, this one is non-binding. The other 3 are binding constraints.